let's suppose you're talking about a tree that's growing, or a blade of grass, okay? Whatever, just some sort of plant growing. Then what happens is it starts at its original growth, okay? We're going to use the number 1 to represent its original growth where it already was, okay? And then as time passes, you're going to add to that, okay? And the way that it grows is it basically takes the part it previously was and gets a little bit bigger. In this case, it's 1/nth bigger. And then as time passes, it's going to have the previous growth, the 1, and then get 1/nth bigger than that previous growth. And then it's going to go from the previous growth and get 1/nth bigger than that, and so on. Now, if you have something growing really, really fast, it may look like it goes from one height immediately to the next. Okay, you look at it at, say, 10 p.m. and then you go to bed and you get up in the morning and go outside and, oh, it looks bigger already. With some really fast growing plants, you can actually see something like that. But it still isn't instantaneous, right? It slowly goes through all of the in-between steps. And it has what's called a continuous growth. And in the natural world, you're going to see that. Okay, and so what that means is instead of, say, jumping from, say, 1 foot to then 2 feet, to then 4 feet, to 8 feet, and so on, what it does is it goes from 1 to 1.1 feet, and then 1.2 feet, and then maybe 1.5 feet, right? It's going to have little spurts in there, right? And so what ends up happening is you have the growth divided into a whole bunch of sub-growth periods, and then over that time, it will get bigger and bigger and bigger, and then reach the point that you see when you come outside your house in the morning and see, oh my gosh, it's so much bigger. And that's what's going on here. And it turns out that if you split those subgroups into more and more pieces, so instead of splitting the 8 hours that you were asleep into just 8 hours, what if you split it into, let's say, all the minutes? So that would be 8 times 6 is 48, so that would be 480 minutes. What if you split it into seconds? So then multiply that by 60 again, which I don't know off the top of my head. Let's use a calculator for that. Okay, so that would be 28,800 seconds. Right? If you kept splitting it into more and more pieces and looking at the growth over that time, what you would find is that the growth rate would be approaching this number here, and this number is called E. That E is for the letter E is the first letter of the last name of mathematician Euler, E-U-L-E-R. And the thing is it's not that this is something that he just picked. He didn't say, I like this number. This is what happens. This is what you get just from nature. And you say, hey, let's divide this into smaller and smaller pieces. And when you do that infinitely many times, you approach this value here. Now, in this case, they've rounded it to, looks like 9 decimal places. But the point is this goes forever. It's an irrational number. Just like pi, right? We often approximate pi to 3.14, but that is just an approximation. That number goes on forever. So, since this is what happens when you look at growth in the natural world, we call it the natural base. And so, when you have f of x equals e to the x, that is the natural exponential function. Here, they've shown a couple different graphs. In this case, they've shown when you have your base is 2. That's this red one here on the right. Okay. Obviously, they switch positions over here, so it doesn't really make sense to say the right unless you're only looking over here. So we'll say it's on the right in the first quadrant. This green one, which is the one on the left in the first quadrant, that's where the base is 3. And this blue one, which is between the two, is when the base is e. And this makes sense because e is approximately 2.7, and 2.7 is between 2 and 3. But like I said, they actually swap positions, right? The red one is now on top in this second quadrant, and the green one is now on the bottom in the second quadrant, but the blue one is still in between them. I'm going to come back to solving exponential equations in a moment, but I want to focus first on talking about the application that relates to that expression we saw before. And that application is compound interest. So the idea behind compound interest is you are gaining interest on previously gained interest, and this is similar to the example I was giving with the growth of a tree, right? When it grows based on how big it was before. So it's going to have the previous place where it left off, and then it's going to get a little bit bigger than that. And so it's the same idea for compound interest. This is the formula you get for that, and I don't know if your teacher wants you to derive that or anything. My guess is no, but that is something that can be talked about separately. Let's focus instead on how we might use this, okay? Because memorizing a formula isn't important. What's important is knowing how it's used. What does it mean, okay? And so, like I said, what it means is you're growing with interest, but that is spread over smaller and smaller pieces, and you gain interest on interest, okay? So what we're going to do here is we're going to write down this formula, okay? We're actually going to write down both of them, and I'll talk about what they mean. And then we'll do an example similar to the one in here, okay? So let's go over to notes over here. So we have compound interest. And so let me write down the formula. Let me tell you where everything is. And then we'll talk about how that relates to the version with E. So what this is referring to is you have some sort of principal. Okay, if you're talking about like an investment, that's your original investment. If you're talking about a loan, that's the original amount you borrow. We also have an interest rate, that's R. It's usually given to you as a percent, and usually people convert it to a decimal when they put it in the formula. Okay, interest rate might be something like, say, 0.82%, right? And then you would convert that to the decimal 0.0082 and put that in for R. Generally assume that is an annual interest rate. If someone wants it to be something other than an annual interest rate, they will have to specify. But if they don't specify, they mean annual. The N, which you see in two places here, that's the number of times interest is compounded over that term, in this case, over a year. The term should always equal whatever your interest rate is over. So this is the number of compoundings per term, and in this case, the term is 1 year. And then T, that's the number of years or the number of terms. The T actually stands for time, not terms, but it's just kind of a nice coincidence that it's also the number of terms. Okay, so if your interest rate was actually monthly, then T would be time in months, N would be the number of compoundings per month, and so on. Okay, so let's look at an example of this. So let's say you borrow $6,500 at an annual interest rate of 3.5% compounded monthly. if you don't pay any of it off and just wait, let's say 6 months, half a year, how much do you owe? Okay. One thing I didn't already mention up here is this A stands for the word amount. And that amount is essentially the future value of your loan or investment, depending on what you're talking about. So in this case, A is exactly the answer to our question, how much do you owe? Okay, so we're going to use our formula here. Our principal in this case is the amount you borrow, so that's $6,500. I'm going to leave off the units for now. We'll put them back in later. The interest rate is 3.5%, which means as a decimal, it's 0.035. It's compounded monthly. Okay, so it's an annual interest rate, compounded monthly. And since there's 12 months in a year, that means the number of compoundings per year is 12. Okay, the number of compoundings is still 12. And the time, remember, it's got to match here the number of years. So 6 months corresponds to half a year, which means T equals 1/2. Okay, so again, P was the principal, that was 6,500. R is the interest rate, that was 3.5%, which is 0.035. N is the number of compoundings, in this case per year. Since there's 12 months in a year, we have 12 for N. And then finally, T was the number of terms, in this case the number of years, because we have an annual interest rate. And so 6 months is half a year, so T is 1/2. Okay, so at this point, let's simplify things just a tiny bit. $12 times 1/2 is 6. Okay, so this is going to be what I put in my calculator, but at this point, you generally do want to switch to the calculator. Now, if you have a calculator that can only do one function at a time, you got to make sure that you do this in the correct order. In this case, you would start with 0.035 and then divide that by 12. And then you would add 1, right? We're just following the order of operations here. And then you would raise that to the 6th power. And then finally, you would multiply that result by 6,500. Okay, so doing this one operation at a time gave me this value. Okay, if I actually have a calculator where I can put it all in at once, so I am going to put it all in at once and see if I get the same thing. I'm going to be careful to make sure I include all my parentheses. And sure enough, I do get the same answer that I got before. So now we're going to interpret the answer for our question. Okay, our question was how much do you owe, which is the amount. And this is generally done in dollars, which means we're going to round it to the hundredths place for the number of cents. So that means you owe, or I owe, depending on how I want to interpret this question, $6,614.58. Okay, so if you were to ask instead of how much do you owe in total, how much interest did you accrue during that time, you would just subtract $6,500 from that $6,614.58. And so you would end up saying that the amount of interest that you owe in addition to the amount you borrowed is $114.58. Going back up to here to this formula, you may notice that if R was 1, right, 100%, and the time was 1 and the principal was 1, we would get the same thing we had back here when we were looking at the creation, I guess not creation, the derivation of what E is. Okay, so if I had R equals 1 and T equals 1 and P equals 1, we would end up with just this expression here. Okay, and so what that means is over here, when we look at our formula for compound interest, if you increase the compoundings more and more and more, what ends up happening is your base ends up approaching the natural base. And this R ends up inside the exponent. It's a little funky because we are doing what's called taking a limit, and that's more of a calculus type question, so we aren't going to dwell on this too much. But the point is if n, the number of compoundings, gets bigger and bigger and bigger, and in fact you say, what happens if I essentially approach infinity, then what you end up with is a function with the natural base. Okay, and so that's what we call continuously compounded interest. In this case, this is for continually compound interest. Okay, and so what that means is continuously compounding means that it's always compounding, meaning the number of compoundings per year is infinity, essentially. You've said it never stops compounding, therefore it's always compounding, and therefore there are infinitely many times it compounds. So when you have infinitely many compoundings, you end up with this as your formula. Everything still has the same meaning. A is still the amount that you either owe or have in your investment. Okay, P is still the principal, which is the amount you initially borrow or invest. R is still the interest rate. And again, if you're not told otherwise, you can assume it's annual. And T is still going to be time, which again, if you aren't told otherwise, will be in years. So let's look at an example. Okay, this time, instead of compounding monthly, it'll be compounding continuously. Okay. So let's go ahead and get rid of some of my extra marks there. Okay, and then so continuously. Okay, so we're still going to use a formula. It's just in this case we use the continuously compounding interest formula. So our principal is still 6,500. Our base is E. Our interest rate is 3.5% and leverage 0.035. And our time is still 1/2 because 6 months is half a year. Okay. So at this point, I'm going to put this in my calculator. If I have a calculator that can only do one calculation at a time, it makes sense to go ahead and multiply the 0.035 and the 1/2 before I start. If I have a calculator where I can plug everything in at once, then I don't really need to do that. Just make sure that you have parentheses around the entire exponent if you're going to put it all in at once. Okay, so if I want to do this one piece at a time, I start by raising e to the 0.0175 power, and then I multiply by 6,500. If I have one that can do everything at once, then I'm just going to do 6,500 times e to the 0.0175 or to the 0.035 times 1/2 all in parentheses. And what I end up with is 6614, so 6,614.751144. It goes on forever, but this is enough to look at for our problem right now. And so the answer to our question, rounding it to the hundredths place again, is you owe $6,614.75. Okay, notice this isn't very different from what we had before, right? 58 cents, 75 cents, that's the only difference. It makes sense that it is a little bit more, because if you're compounding it more often, then you're going to have more of the interest gained on previously gained interest. But the fact is, it's not that much more, because we're not talking about a very long period of time. We're not talking about a whole lot of money. But if this was a lot more money and a lot longer period of time, then you're going to see a bigger difference between the two. Okay. The other applications you'll see in here, basically, they deal with another natural growth exponential equation, but it has this coefficient out in front, okay? And the reason why is because that's going to be your initial value, okay? If we have A equals, we say A naught, N-A-U-G-H-T. It's just another word for zero. Okay, A naught, e to the RT. And the reason we use A naught, okay, it's basically saying the initial amount. So if this is describing a population, like a population of rabbits or something, then A naught will be the initial population that you were looking at. Okay, so if you start looking at it on January 1st, then that's the population on January 1st. If this is talking about maybe the amount of a radioactive element, then this will be the amount you start with before you start watching it decay. Okay. The R is the growth or decay rate. Okay, so it's essentially like an interest rate. It's just more general. Interest is specifically for money, but you can have all sorts of growth rates and decay rates. Okay, and T is still going to be time. Okay, and so let's just take a look at this example here. Here we have a researcher, and this researcher is trying to understand the behavior of a new and dangerous virus. This is very topical, right? He starts his experiment with 100 of the virus, okay? So what he means, what this means is he has 100 individuals. The population that he starts with is 100. So earlier I was talking about the initial population, if you're looking at a population growth, and that's what we're looking at here. And so since the initial amount is 100, that's our value for A naught. Let's see why that makes sense. Let's suppose I let T equal 0. So no time has passed. Then we would have A equals A naught times e to the R times 0. Well, R times 0 is 0. E is, remember, that's just a real number. It's positive. It's between 2 and 3. And so raising this positive number to the 0 power is 1. And something times 1 is itself. So we have, when t equals 0, the output is precisely whatever this coefficient is, this A naught. So, going back to this problem, no time had passed. He started the experiment with 100, so that means A naught is 100. That's going to be that coefficient out in front. We're told in here that it grows at a rate of 25% per hour. So that's kind of like an interest rate of 25%, but instead of an annual rate, it's an hourly rate. Okay, so that R is 0.25 for 25%, and T is going to be a number of hours. So he's going to check on this virus a day later, 24 hours later. So how many will he find? Now, of course, in the real world, things happen. Like you might have some of them die. The viruses aren't quite alive, but we're just going to say they might die. Okay, cease functioning essentially. But this is essentially saying how many should he expect to find. And so if you substitute all these values in, 100 for A naught, 0.25 for R, 24 for T, and evaluate it, you're going to get something close to 40,342 and 88 hundredths. Okay, since we're talking about a number of viruses, you would round this up to the 3 here in the ones place. Okay. Again, this is just a prediction. They should probably say the researcher expects to find this many viruses, but we'll forgive them for that that lapse in precision. I mentioned radioactive decay. That there is a link in here to something about radioactive decay. I believe it's a YouTube video. Yes, it is. And so you can go ahead and find more about that, and you can see more examples of some of the stuff we've already seen.